just a heads up, we're having a bit of a challenging day here in my house. One of my kids is sick at home. My parents were going to help out, and my dad is having some sort of a procedure. He went to the doctor today, and they're like, "Oh, we got to do something." So, not quite sure what's going on there. But as a result, I've got my little guy, Luca, over here. He's kind of playing in the room with me. So if I need to attend to him momentarily, apologize in advance for that interruption. Okay. So, all right. So let's start with this idea. What if you are given a claim and it's actually false? Claim. For all integers n is less than or equal to n cubed. Is actually false. Okay. N is not always less than or equal to n cubed. So in order to disprove, so what we can do here is instead of proving this, we can disprove it. If you want to disprove a proposition, what you do is you prove its negation. That's what it means to disprove something. Makes sense, right? You want to prove it's false, so prove that its negation is true. That's all. So let's negate the claim. Oh. So all we got to do is negate this claim. Okay. It was for all integers n. If we're going to negate that, it's going to become there exists an integer. Oops. Uh-oh. No, you can't take the mouse. That's going to be a problem. Mm-hmm. So instead of for all integers n, it's now going to be there exists an integer n such that, and then all I need to do is negate this, right? The negation of n is less than or equal to n cubed. What happens when you negate less than or equal to? You get greater than. So I'll write n is greater than n cubed. Okay, so that's our negation. So now I want to prove this negation. And this negation is simply an existence claim. So proving an existence claim is pretty easy. As I mentioned yesterday with the example, remember how we were proving something exists? It was like prove that there exists a real number whose square is not positive. And we're like, oh, 0. 0 is not a positive number. It's 0. And 0 squared is 0. Right? So we proved that by exhibiting a case when it happens. So what we want to do here is see if we can find an example of an integer whose cube is less than it itself. Can anyone think of an example? There's actually a lot of examples. Sorry, go ahead.
A negative number?
That's right. A negative number. Consider n equals something like -2. Then n cubed equals -2 cubed, which is -8. And -2 is greater than -8. Thus, such an integer exists. Done. The original claim was false. Okay. So, so sometimes sometimes you can disprove something. You can disprove a for all statement with an example. This is called a counterexample. Okay. I hear you, Luca. Yeah. Okay. So, there's an example. That example was disproving a for all statement using a counterexample. Let's look at another one. For this one, yep, let's look at the claim. There exists an integer n such that 2n equals 5. This is also false, right? There's no integer that when you double it, you get 5, right? Because 5 is not an even number, 5 is an odd number. So if we want to disprove this, we can, first of all, state its negation. I got to do something for Luca here. Hang on, guys. Right. So how can we negate there exists an integer such that 2n equals 5? Well, when you negate there exists, you get for all, right? For all integers n, I guess 2n is not equal to 5, right? So it's a little harder to disprove an existence claim because when you negate there exists, you get for all. And now the thing we need to prove is much more broad, right? Instead of disproving this by just proving it exists, like in the previous example, which we can do just by showing like, hey, here's an example, ta-da, done. With this one, it's like, oh, now we need to prove that you, like, this is kind of broad. You never get 2n is not equal to 5, right? That's kind of intense. But luckily, we have this thing called proof by contradiction. Right? So if disproving something is proving its negation, you can prove the negation by contradiction, which means you start by assuming the original claim, right? So let's go back to the original thing, because that's the negation of the negation, right? So you can say, all right, we'll disprove it by assuming it's true, and then deducing a contradiction from that. So we're going to say, well, sure, assume there does exist an integer n such that 2n equals 5. Well, then n would have to equal 5 divided by 2, but 5 halves is not an integer. That was kind of easy. this contradicts the assumption that n is an integer. So that was fairly easy too, but it's just a matter of like thinking through the logic, right? What is the strategy here? What exactly are we doing? Okay, so these are a couple examples of disproving things, and both of these examples are sort of, they both involve this De Morgan's laws for quantifiers, right? When you negate for all, you get there exists. When you negate there exists, you get for all, right? It kind of like they kind of go back and forth. Okay, so part of what we're dealing with here is a thing called an existence proof. So let's talk about existence proofs in a little more specifically. I'm going to go ahead and get a fresh page for this one. Here we go. So existence proofs. One way to do an existence proof is what's called constructive. Okay, you exhibit an element of the domain for which it's true. This is what we did with the examples we've seen so far, right? With showing that there's an integer whose cube is less than it. You're like, oh, take a negative number. Like, we could have picked any negative number, or not any negative number, but a lot of different possible negative numbers. Like negative 2 worked great, right? Negative 2 cubed. There you go. It's an example. That's a constructive proof, but there are also non-constructive proofs. Which is anything else. Non-constructive proof is just any proof any proof of existence where you don't actually end up with an example when you're done. Like, you just don't have one. It's not there. I want to show you a fun example of a non-constructive existence proof. And then we'll prove the same thing constructively. Okay, so this proof that we're going to do is going to rely on another fact, which I'll call a lemma here. If I introduce the word lemma, I saw a nod. If you don't remember what a lemma is basically a theorem. It's like a little theorem. Yeah, it's a little theorem that you are going to use to support a later theorem, right? The theorem here I want to say is just the square root of 2 is irrational. That's all. There's a famous proof that the square root of 2 is an irrational number. I considered going over it with you guys the other day, but I felt like we didn't have enough time. It's kind of long. I'm not going to go over it right now either, because I want to show you this other example of an existence proof. But yeah, sometime I recommend looking up the proof that the square root of 2 is irrational. It's quite nice. It's proof by contradiction. But here's the example we're going to do today. There exist real numbers. Oh, sorry. Irrational real numbers, x and y, such that x to the power y is rational, not irrational. Okay, oops. Proof. There exist irrational real numbers, x and y, such that x to the power y is rational. Okay. This proof is going to use cases. One of the proof strategies that's introduced in section 1.8 is to break things down into cases. If you could break things down into cases and exactly one of those cases must be true, as long as the cases kind of cover all the possible true situations, all the possibilities, I guess, then you can prove it in each case. And each case gives you something to assume, which can be useful to work with. This proof is going to center around a specific number. Consider the number the square root of 2 to the power square root of 2. Okay. This is a real number. And thus, it must be rational or irrational. Does anyone know if that number is rational or irrational? The square root of 2 to the power square root of 2. Is anyone plugging it into a calculator right now?
Throwing on a whiteboard, not onto a calculator.
If we do plug it into a calculator, by the way, you get this square root of 2 to the power square root of 2. It gives you a decimal expansion truncated after however many digits your calculator will allow. This looks irrational, but maybe there is a repeating pattern here. It's a very long repeating pattern. Like maybe there's all these numbers and then it starts repeating at some point later on, right? Like just looking at this and seeing, I do not see a pattern within the first 12 digits. That's not a proof that it's irrational, right? By the way, what I'm doing when I refer to a pattern here is I'm talking about that equivalent notion of a rational number, which is equivalent to being a ratio of integers. You can also say that its decimal expansion has either truncates, either like ends, or it has a repeating pattern in it. That is another characterization of rational numbers. So anyway, I am pretty certain that this number is irrational, but I'm not exactly sure how to prove that it's irrational. It certainly looks irrational. But interestingly, for the purposes of this proof, we don't need to know whether this number is rational or irrational. And I'll show you why. We're going to consider those two possibilities as cases. So, case 1. Suppose that the square root of 2 to the power of square root of 2 is a rational number. As we have stated, this is probably not true. It's probably irrational. But what if it were rational? At least in that case, if that were the case, then since we do know that the square root of 2 itself is irrational, what we can do is let x equal the square root of 2 and also let y equal the square root of 2. X and y are supposed to be irrational numbers, right? There exist irrational numbers, x and y. Nobody said they couldn't be the same number. Okay. Then x to the power y is square root of 2 to the power square root of 2 is rational. So the claim is true. Such a case does exist. in this situation, right? In this case one, where square root of 2 to the power square root of 2 is assumed to be a rational number. So in this case, that would be an example to prove the existence claim. But we don't know for sure that we're in that case. So let's now address the other case, case 2. Suppose that square root of 2 to the power square root of 2 is irrational. Okay, in this case, we're going to find an example again. We're going to prove the existence by example again, but we're going to choose a different example. Then let x equal that number, which is irrational in this case, right? In this version of the universe. So let x equal that number, and let y equal the square root of 2, which, as stated earlier, is irrational. We're relying on that. Okay. So now in this version of events, x to the power y equals square root of 2 to the power square root of 2, and then all of that to the power square root of 2. What happens when you take like a power of an exponential expression? What do you do with the powers? Multiply them together, right? You guys remember that? A to the power b to the power c. You like multiply the powers together. So this is square root of 2 to the power square root of 2 times itself, so squared. In other words, this is the square root of 2 squared, which is 2, which is rational. Oh my goodness.
Isn't that faulty there?
Why is it faulty?
Square root of oh wait, nope, never mind, I'm wrong.
Squaring the square root of 2 gives you 2. Okay. So again, the claim is true. So then what we can say at the end is, in either case, the claim can be proven true. So the claim must be true. And the proof is done. I'll put a QED at the end. But now, tell me, can you tell me an example of two irrational numbers where one raised to the power of the other equals a rational number? At this point, do you have an example right now? At the end of this proof, do we have one in our hands that we can hold up and say, look at this. Here's an example to prove the existence. You don't. All you have is two cases, one of which must be true. And in either of those cases, we've shown that it is possible to find such an example. But we don't know which of those two examples is actually like correct. You know, which of those two examples is actually the example? We don't know. I mean, my money's on this one, right? Because I think that number is probably irrational. So I think this is the case that's true. I think case 2 is the real world, right? And case 1 is false. But like, that's not what I proved. I proved that in either case, you can prove the existence. But I didn't actually exhibit a example, right? So that's why this is called a non-constructive proof. Okay, non-constructive. We did not construct an example. It is possible to prove this claim in a constructive way. Does anyone know an example of X and Y that are both irrational, where if you raise one to the power of the other, you get a rational number, guaranteed? Curious if anybody can think of such a thing. I'll give you one. E natural log of 2. It can be proven that E is an irrational number. This is pretty well established. And the natural log of 2 is also an irrational number. So like how I was, like how my first version relied on the fact that square root of 2 is irrational, this proof is going to rely on these other facts that these two numbers are also irrational. But if you go x to the power y, that's e to the power natural log of 2. And that is a composition of inverse functions. The e, the exponential function base e, and the natural log is a base e. They cancel out and you get 2 again. So that would be, I didn't write that up cleanly because I only had like a little tiny bit of space at the bottom of the page here. But that would be a constructive proof of this fact, where you actually have an example in your hands and you can say, look, here it is. John asks a great question. Is a non-constructive proof a bad way of proving things? Very interesting question. I mean, so let me be very clear. It is a valid proof. The first non-constructive proof is valid. Like, it does prove that there exist these things, like, is it a bad way? Maybe it's not as good. That gets into, there's different ways to evaluate a proof. You can evaluate a proof on its like logical correctness. And if you're just evaluating it based on its logical correctness, these are both logically correct and valid. But you can also evaluate a proof based on its sort of value, and maybe like it's sort of how it makes you feel or what it contributes to your knowledge, like other than just that the claim is true, like I feel like the second one is a little more valuable because it not only does it prove the claim, it also provides an example that you can show people, right? And that's so I think that there's sort of a subjective way to discuss the value of a proof, and this is something that mathematicians like to talk about a lot. They definitely there is definitely a sort of like an opinion among mathematicians that some proofs are better than others just because they not only prove the claim, but they also explain it, right? If you come away from the proof feeling like you understand why it's true, not only just are convinced that it is true, then that's better. Very interesting discussion. Yeah. So let's see. I'll put that away. That'll be page 2 there. Okay. So what else can we do? I mentioned yesterday that we did this example about, 0 is an example of a number whose square is not positive. But the way it was written on the paper I handed out to you guys says there exists a unique real number whose square is not positive. Let's talk about that uniqueness. Okay, so a proof like this exists a unique. Unique means that there's only one, right? A proof like this needs to be done in 2 parts. So the first part is the existence part. We did this yesterday. It was constructive using 0 as the example. All right, so we did that yesterday. Now we will address the uniqueness claim. So I guess I'll call this like the uniqueness part. Okay. So to prove that 0 is the unique number, real number, whose square is not positive, we need to suppose that there is another example that isn't equal to 0. So we'll say, suppose a squared is not positive, less than or equal to 0, for some real a, which itself is something other than 0. Okay. And the proof we're going to do here, the proof of uniqueness, is actually a proof by contradiction again. It's a proof by contradiction because what we're doing right here is assuming the negation of the uniqueness. We're assuming that it's not unique. We're assuming that there exists another example besides 0. And then what we want to do is derive some contradiction from that. Okay. I think it's sort of hard to see how to do this, but I think cases might be good. If a is not 0, then either a is less than 0 or a is greater than 0. And we can kind of rely on our very basic understanding of like arithmetic here. We can say, you know, if a is less than 0, then a squared, which is a times a, is going to be a negative times negative, which equals a positive number, which is positive, right? So like this, I'm being a little informal here, but this is like one of those cases where I want to just like appeal to something we learned about arithmetic a long time ago that we're going to take for granted. We're going to take it as given that a negative times a negative number is a positive number, right? And then of course, if it's positive, then a squared is positive times positive, which also equals positive, right? So in either case, you have a positive number, right? So this contradicts the assumption a squared less than or equal to 0. So yeah, so 0 is the only one. That's this is not a great example, I guess, because this part of it is a little bit weak. I feel like it's almost one of these things where it's so intuitive. It's like so obvious that proving it feels weird at all, because it's like, well, it's just true. But what I want you to focus on is more so like the strategy that we're employing here, right? First of all, we're breaking it into the two parts. We're breaking it into prove existence, prove uniqueness. When you're proving existence, it's just existence. You don't need to think about uniqueness. It's just show that it exists. An example will suffice. Uniqueness is where you say, okay, so now that you got that example, let's suppose there's another one. Contradiction. Okay. Which shows that example must be the only one. So that's so yeah, like I said, it's a strategy that I'm more concerned with here, that I'm trying to demonstrate, more so than like the actual like example itself. Okay. Okay. Any questions? Because otherwise we can move on to another example. We've been talking about proving existence, looking at examples of using contradiction, proving uniqueness, using cases. We've got another example coming up that uses cases and also relies on symmetry. So you guys want to see the next one? Or am I moving too fast? I see some okays. Let's do it. Okay, so the next one, this next one, by the way, is in the textbook. I apologize. Some of these examples are in the textbook. Others of them are not. I kind of, I sometimes do my own thing, and sometimes I do what the book does. Whenever n and m are integers with opposite parity, which parity is the quality of being, odd or even. Okay, so basically it means one of them is odd and the other one is even. Whenever n and m are integers with opposite parity, 5n plus 5m is an odd integer. I'm just going to say is odd. The fact that it's an integer is pretty well established already. Right? It's closed under, integers are closed under a multiplication and addition. So I'm not going to really worry about that integer part. Let's just show that it's odd. So whenever n and m are integers with opposite parity. Now, technically, there are two cases here. Technically, two cases. One, n is odd and m is even. Two, n is even and m is odd. If we were being exhaustive, which is a word mathematicians use to say that you're like covering all of the possible cases, and often that's used when there's like a lot of cases. If we were being very exhaustive about making sure we check all the boxes and cover all the bases, we would address both of these examples. But we can be a little bit clever and recognize that there is symmetry in this expression. By symmetry, I mean that you could swap n and m and it would remain the same, right? So which of them is odd and which of them is even doesn't matter, right? So we're gonna lean on that symmetry. So I'm going to say there is symmetry in this expression 5n plus 5m that makes these two cases identical. And so we're going to begin our proof by saying, assume, and then I'll introduce this cool phrase, without loss of generality. That n is odd and m is even. So this phrase, without loss of generality, is used usually when you have some kind of symmetry such that there are multiple cases, but they are the same. Right? There's multiple cases, but they are effectively identical. That's, you can say, without loss of generality, let's consider one of these cases. And that phrase is sort of a cue that you don't need to consider the other cases because they're the same. So just specifying one particular case remains the result of your proof will be just as general as it was if you had gone through all the cases individually. So this is a phrase that mathematicians use to kind of cut corners, right? And be like, well, we don't need to consider those other cases. We just got to look at this one and this will be fine. It's a phrase you want to be really careful with. You can only use it in certain situations. You got to be really cautious when using without loss of generality. But it is something that comes up in a lot of proofs that you'll read. So we're going to use it here. And we can say, let's wrap up this proof then. The rest of this proof is quite easy, right? It's just this very beginning kind of examining the cases and kind of cutting them in half and saying, let's just look at one. The logic of that is the main purpose of this example. But the rest of it, we'll finish it up. The rest of it is nice and quick. We can say, well, then n equals, if n is odd, it's like 2k plus 1 for some integer k. There's k in z. That means it's an integer, right? Remember, that's the sign for, it's a symbol for integers. And then m, since it's even, is like 2 times some other integer. So I can't use k again. I got to use a different number. So 2l for some l in z. Okie doke. So I have 2k plus 1 and 2l. And so now I can plug those into the expression 5n plus 5m and get 5 times 2k plus 1 plus 5 times 2l. And what I get out of that is 10k plus 5 plus 10l, which I can kind of maneuver around a little bit. That's like 10k plus 10l plus 4 plus 1. It's interesting, you could take your 5 and you split it into a 4 and a 1. Kind of an obvious thing to do, but some things like that are so obvious you might not even ever think to do them. You know what I mean? All we want to have is a plus 1 at the end, right? Because our goal is to prove that this is odd. That was the claim, right? Was this yeah, we want to prove that 5n plus 5m is odd. So I got to get that little plus 1 at the end. And so I just take it off of the 5, which leaves 4. But then that's nice because all of this is even. So I can factor a 2 out of the rest of that there. And then I can do my wrap up like I usually do here. Since 5k plus 5l plus 2 is an integer, this shows, that should be a comma, not a period. This shows that 5n plus 5m is odd. And we're done. Symmetry, without loss of generality. This proof is about half as long as it needed to be, or half as long as it could have been. Half as long as it needed to be. If it was half as long as it needed to be, then it wouldn't be complete. No, it's half as long as it could have been if I hadn't used without loss of generality, because we would have had to flip it around and say, all right, now let's see what happens if n is the even one and m is the odd one, and it would be exactly the same, and we would be bored. But that's the point of the without loss of generality. We can just do one, and hopefully the reader agrees that we didn't need to do the other one.
Isn't the part that it says since 5k plus 5l plus 2, aren't you missing the 1 at the end, or?
Aha, no, I didn't. I intended to take that out. So the idea here is this is 2 times something plus 1. An odd number, the definition is 2 times an integer plus 1. So as long as the something inside here is an integer, then this expression is an odd integer.
Okay, gotcha.
Yeah. I was very intentionally just extracting that part of it to point out that's an integer in there, right? Because you're taking integers, you're multiplying them and adding them together. Still an integer. Oops. Okay, how we doing? It's 10:47. We're just about out of time. I think that'll do pretty good today. So you guys have a couple of proofs on your exercise set 2, which you guys are working on, and I've been answering questions in office hours about exercise set 2. Don't forget that you're welcome to ask me questions. There may or may not be, you guys, have we ever talked about whether there's any tutors at the ASC who can help with discrete math?
Nope, we have not.
We haven't talked about that. I want to say Iman took discrete math with me. Do you guys know Iman Hamden? She's the tutor for Calc 2. She was the tutor for Calc 1. Or like, not the tutor, she was the SI for Calc 1, if anybody was with me that last semester. Iman Hamden is there, and I think I'm pretty sure she took discrete with me last year. So I think she can help with that. I may be misremembering. Iman has taken a number of different classes with me, and I may have forgotten which ones it was. I know she took Calc 1 and 2 and linear algebra. I think she was in discrete. But I don't really know anybody else. I don't know anybody else who's working there at the moment. But I will look into that for you guys and see if I can find any tutors. But in the meantime, you're always welcome to ask me. And if you're not sure what to do, just do the best you can. Because remember, the main point of these exercise sets is for me to be able to look at your work and give you feedback. So please just do the best you can to write a good proof. And then the more earnest of a try you give it, I think the more genuine and helpful my feedback can be. Okay, because if you just kind of half-ass it or skip it entirely, well then I won't be able to give you much in the way of constructive feedback if you just write like a couple of lines. Telling you how to do it is not feedback. Right, telling you how to do it is different. So if you leave it blank, I'm not gonna just tell you how to do it. I might give you a little push in the right direction, but mainly the purpose of this is to give me feedback on your work. Okay, so please try to do that, and don't worry too much about the grades, because I know that's part of it here, but the main purpose is the learning. Okay. So, have a good one, folks. I will see you all anon next week.
A quick question.
Oh, sure. Yeah, go ahead.
So office hours is after class, right?
Yeah, we can do that right now.
All right.
Stop the
So
recording.
should I just stay?